I'm Jake O'Neill, creator of Animagraphs, and this is how a diesel-electric, heavy-haul freight locomotive works. Diesel-electric locomotives have remained popular for over 60 years. As a measurement of capacity, they can take a 2,000-pound chunk of freight nearly 500 miles on 1 gallon of fuel, which is 3 to 4 times more efficient than a semi-trailer truck. Let's start with the body and frame. Most modern freight locomotives are hood units with a slim middle section and walkways on the outside of the body, allowing visibility in both directions. The nose portion is full width or wide cab. Locomotives mostly run short hood first, as designated by the decal letter F for front. Metal body panels can be opened or removed for maintenance or emergency access. Main sections are the nose and operator's cab, auxiliary or aux cab, which is packed with electronic components, the engine, and radiator cab at the rear with various cooling components and the onboard air compressor. The body and critical components are supported by a thick steel or steel alloy platform called the underframe. A pilot or cowcatcher sits at the front to deflect obstacles that could derail or damage the locomotive. There's an overhang called the anti-climber that prevents deflected objects from flying into the cabin. Concealed collision posts on each side further protect the cab in the event of an accident. There's a unique ID number displayed on the front and sides. A set of air horns sits on top of the body, and there's an electronic speaker attached to the underframe to emit a bell sound. A large manual handbrake wheel is visible near the rear. Coupling. Locomotives can couple with other locomotives or train cars. There are various coupler types. Our locomotive has a more complex Type F coupler, versus the simpler Type E style on our train car. Type F, for example, has robust side features to prevent vertical movement in accident conditions, where Type E requires no such protections. Couplers are designed to work by bumping into one another. They'll couple in various arrangements, for example with both couplers open, or one closed and one open. As knuckles make contact, their rounded shape causes rotation that presses against the knuckle thrower. Which in turn moves the lock. The lock rides along an internal channel and also rests on a sloped feature at the back of the knuckle, so that it naturally slides into locking position as all parts reach the end of their travel. For uncoupling, there's a manually operated bar called the pin lifter or cut lever. When rotated, parts operate in a reverse sequence to coupling. The lock rides upwards, pressing the knuckle thrower, which rotates the knuckle into open position. The coupler is attached to the draft gear assembly, which provides a kind of suspension between train cars. During impact coupling, also known as a buff event, the coupler is forced backwards against the draft gear, which compresses an internal stack of rubbery discs. The draft gear's rearward travel is stopped by thick metal tabs at the back. When train cars pull away from each other, also called a draft event, the surrounding yoke pulls the draft gear against a block at the front, causing the internal discs to again compress and absorb potentially harmful forces. When cars are coupled together, a hose is also connected to supply air for individual car brakes, and a cable for cars equipped with electronic brake support devices. More about these systems later. When multiple locomotives are coupled, the MU, or multiple unit connector, brings mechanical, engine, and electrical systems under control of the lead locomotive. The connector sits in a dummy receptacle when not in use. 3 additional hoses synchronize braking operations between locomotives. There's the main reservoir hose, the actuating hose, and the brake cylinder hose. Engine. A 12-cylinder, twin-turbo, 4-stroke diesel engine, called the prime mover, is the power source for this locomotive. Fuel is supplied from reinforced wall tanks mounted beneath the underframe. These tanks can carry 5,300 gallons of fuel. The fuel injection system has a pump for each cylinder bank, with multi-walled tubing between cylinders designed to handle high pressure. To decrease noise levels and increase efficiency, as many as 8 different injections of fuel are made during a single combustion cycle, as determined by sensors in the fuel system. Engine support components are mounted nearby, including a lube oil tank and oil filters, fuel filters, and more. Turbocharging. This engine has 2 turbochargers to efficiently supply the engine with more air for combustion. There's a charge air cooler nearby to cool turbo air before it reaches the engine, since cold air is more dense and better suited to the goal of pumping more air into the engine. The charge air cooler has 2 sides, one for each turbo. These turbos are arranged in what's called a compound sequential configuration, which functions as follows. At lower RPMs, exhaust gases can more easily spin up the smaller turbo, whose compressor wheel begins to take in air. Air enters through a side port and flows through the large turbo before entering the small turbo. It's then cooled on its way to the engine intake. The large turbo is not yet fully powered. As RPMs and resulting available exhaust energy increase, a valve opens, spinning up the large turbo. While the small turbo is easier to rotate at lower RPMs, it's also designed to handle higher overall pressures. As such, the large, low-pressure turbo now directly feeds all of its air to the smaller, high-pressure turbo, and the whole system delivers maximum airflow to the engine for peak performance. To dramatically reduce certain pollutants and exhaust gases, these diesel engines are equipped with an EGR, or exhaust gas recirculation system. A valve allows exhaust from the left cylinder bank to enter the EGR system, where it passes through a water cooling unit before being mixed with fresh incoming air. Sending some exhaust gas back through the combustion process lowers combustion efficiency in favor of greatly reducing exhaust pollutants overall. Water. To save costs and avoid potentially hazardous antifreeze leaks, water is used for various cooling duties. A large tank holds nearly 400 gallons of water. An engine-driven water pump supplies pressure to the system. There are large banks of radiators with external shutters to help manage airflow. An oversized fan pulls outside air past these radiators as water courses through internal tubes. This cooling water flows to the engine, EGR cooler, turbochargers, air compressor, and more. During cold weather, it also runs through the fuel system preheater to warm the fuel before combustion. If the locomotive is not running and temperatures drop below 40 degrees Fahrenheit, automatic water dump valves open, draining the system to prevent freezing. Electrical. The diesel engine turns a massive alternator which acts as a generator, supplying electrical power to critical systems. The alternator has its own dedicated blower for cooling with a side air intake. The locomotive isn't directly mechanically driven by the engine. Instead, large electrical motors, called traction motors, are connected at each wheel axle and provide the main driving force to move the train. These traction motors require fine-tuned speed control. Without getting into too much detail, it's simply easier to regulate variable motor speed with DC current as opposed to AC. As such, a fairly intricate conversion process takes place from the alternator to the traction motors. AC power from the alternator is converted to DC power as it flows through rectifier banks in the auxiliary cab section of the locomotive. A DC link in the same system smooths out any uneven power from the alternator and adjusts power to the desired speed or frequency. Current then flows through inverters, which convert it back to AC as it's delivered to the motors. New technology makes varying AC current more doable, and this process may change in the near future. These traction motors generate a lot of heat during operation. There's a dedicated air blower system with ducting and flexible connections to deliver cooling air to each individual motor. Banks of batteries sit underneath the aux cab. Apart from expectable battery duties like starting the diesel engine, these batteries can also deliver power for moving the locomotive small distances, for example around a rail yard, without having to start the diesel engine. Trucks. The underframe rides on trucks or bogies, which hold traction motors, axles, wheels, and associated components. A major consideration in truck design is adhesion, or ensuring wheels maintain maximum contact with rails for traction. Primary suspension aids adhesion with springs on both sides of every axle. A pair of dampers on one side are sufficient to handle vertical shock absorbing duties for the bogie. Secondary suspension includes a set of dampers for rotation about the vertical axis. Flexible side bearers are pinned to the underframe but allow bogies to shift underneath the heavy locomotive. Inside, there's a stack of rubber pieces that make up a kind of tough spring. Axles can also move back and forth slightly. This, with secondary suspension, ensures bogies and wheels maintain maximum rail contact, even when the front and back of the long locomotive aren't in alignment. Or on curved sections of track, where front and back trucks and axles within the trucks might need specific individual orientation to keep proper contact with rails. A traction pin or rod solidifies the connection between trucks and the underframe. Safety hooks limit bogie movement at extremes. The traction motors are attached with bracketry that allows the motor to move with the axle. A gear set transfers motor power to the axle and wheels. The trucks also feature a sand system for increased traction during startup or braking, or when traveling at less than 15 miles per hour. There are sand boxes at both sides, front and back, with filler tubes for easy access. Sand nozzles at the front and back of each bogie provide sand for either forward or reverse travel. the nozzles blow sand at the wheels and rail when in use. Braking. The ability to efficiently haul incredible tonnage comes with a serious technical challenge: stopping the train. There are two main systems for braking: dynamic and pneumatic. Let's start with the pneumatic or air-driven system, which actuates brake shoes at the wheels. The onboard air compressor supplies compressed air which is stored in side tanks. The brake system draws from these reservoirs. Air-driven cylinders at the front and back of the trucks actuate rods and linkages that drive brake shoes. One cylinder manages a single shoe, while another cylinder drives two linked shoes at once. Still, there's only one brake shoe per wheel. At the rear of the locomotive, there's a brake pipe that delivers compressed air to every other rail car in the train. Each car has its own air reservoir to make sure there's always supply for the individual car's braking needs. Modern locomotives have electronically controlled pneumatic or ECP systems where electronics add precision control to braking procedures. The brains of the system are mounted underneath the cab. Each car has an identifying unit and controller setup. There's an end-of-train device connected to identify the very last car. With all cars connected and properly sequenced by the ECP system, more complex braking procedures can be performed. For example, brakes can be applied progressively from the last car in the train forward so cars don't ram into each other. Now, let's look at the dynamic braking system. Dynamic braking happens inside the powerful electric traction motors. To put electric motors in basic terms, the core or rotor has a stationary magnetic field. It's surrounded by a dense set of electrical windings called the stator. Electricity traveling through a conductive material creates a surrounding magnetic field. The flow of electricity through the windings causes its magnetic field to rotate, pushing the rotor in turn. Since the stator's magnetic field is electronically generated, it can be controlled and even reversed, adding resistance against the rotor's spin. This added resistance essentially converts traction motors into electricity generators. The excess energy is passed to grids of resistors that bleed off braking energy in the form of intense heat. The dynamic brake box isolates resistors into their own ducted channel with cooling fans. Resistors can get so hot they emit a bright red glow. Dynamic braking adds stopping power to the train's braking process with few additional moving parts, reducing wear and tear all around. This dynamic braking process shares concepts with regenerative braking, where electric vehicles can use their momentum to recover energy for battery recharging and so on. Future freight locomotives may indeed implement such capabilities to the dynamic braking system instead of releasing this energy as heat. Locomotives generally use a blended braking approach, with both pneumatic and dynamic systems playing a carefully orchestrated role in stopping the train. Now let's head to the front of the locomotive for a tour of the nose and operator's cab. A door at the nose cab allows entry. Off to one side, there's an electronics cabinet with a head of train device which complements the end of train device. There's an event recorder, a distributed power system radio module that gives remote control over locomotives that are part of the train, but not directly connected to the lead locomotive. There's a yard download radio, which allows wireless event recorder data downloading, and a GPS module. At the other side of the entry hallway, there's a bathroom. And next to that, a small refrigerator. Climbing the stairs into the operator's cabin, there are switches for internal lights. From the back of the cabin, we can see the operator's console and a crew member's console at the other side. Let's have a closer look at the operator's controls. There are two smart displays that can show detailed monitoring of critical systems, with rows of buttons at the bottom for interaction. Below that, the alerter button is part of a safety system to ensure driver alertness. The alerter system sounds every few minutes or so, depending on locomotive speed. If the alerter button is not pressed within a number of seconds, brakes are automatically applied. The horn sequencer button sounds the bell and horn together at predetermined intervals if traveling at more than 0.5 miles per hour. Individual bell and horn buttons are nearby. A switch panel houses various controls, for example, the dynamic brake switch to toggle the system on or off. This switch is on for the lead locomotive, but off for other locomotives being controlled by the lead. Many other settings follow this pattern in different lead or trailing configurations. The gauge light controls lighting for various operator controls. The call switch sounds an alarm bell in the operator cabs of trailing locomotives. The reverser handle controls which direction the locomotive will move when power is applied. The handle is removed when the locomotive is parked or in helper duty following a lead locomotive. The reverser handle has built-in constraints to prevent damage. The throttle lever above can't be moved from the idle position until the reverser lever is moved from its center position. Conversely, if the throttle is set at more than idle speed, the reverser handle cannot be moved from its forward or reverse position. The handle is also locked if dynamic braking is not off. The throttle handle manages engine speed and power output to the wheels. It's essentially the train's gas pedal, where a steady, consistent power output setting is ideal for most train operations. The dynamic braking handle controls dynamic braking force. There are redundant buttons for the horn, alerter, and bell. There are also controls for the sand system. There's a two-way radio receiver nearby. The lever beneath controls the pneumatic brake system. There are various settings to manage brake system air pressure in the locomotive itself and connected cars. The independent brake lever below controls air brakes for just this locomotive. There are rotating switches at the bottom of the panel for the cab heater and also front and rear headlight controls. Moving to the back wall, there's an additional fold-out seat. Above that, a grouping of circuit breaker modules and switches. In the middle, there's a protected engine control panel. Let's look at the engine control switch. For locomotives so equipped, the jog setting allows movement under battery power alone without starting the engine. It's used for short distances, like moving in or out of a repair shop. With start selected, the engine start button is pressed to initiate the engine start sequence. Isolate leaves the engine running at idle but disconnects the main generator and power to the wheels, etc. The run setting is for normal operation. The multiple unit switch has settings for linking multiple locomotives together in various configurations. There are engine start and stop switches, and the last panel controls crosswalk or ditch lights at the front of the unit, number sign lights, and lighting for other control areas. The auto stop override button prevents the engine from shutting down automatically for 2 hours. Now let's move to the crew members area. There's an additional ergonomic seat for observing, training, and other purposes. There's a smart display at the left side of the crew member's console. In the center, the emergency brake valve initiates an emergency braking sequence. At the front of the console, there's a horn push button and a heater control switch. Looking towards the front windshield, we see inward and outward facing cameras for event recording.